Hi, my name is Heinz Frey. I'm a senior scientist at Lawrence Berkeley National Laboratory. Slowing down climate change is the major challenge for society of our time. This means, above all, that we need to keep fossil carbon in the ground. Fossil carbon is coal, oil, and natural gas. These are the overwhelming source of climate-changing carbon dioxide. Now, for making a renewable fuel with sunlight, artificial photosynthesis, on a sufficiently massive scale so that it has impact on slowing down climate change, and for making large-scale industrial chemicals in an environmentally sustainable way, water is really the only chemical source of electrons and protons we need to make these chemicals. Earth-abundant metal oxides, like for example of iron, so that is rust, of cobalt, manganese, nickel, have in recent years really become the favorite catalyst materials because we have enough of them, they are robust, and intense research is gradually increasing the efficiency. Detailed mechanistic understanding of the catalysis is very important for improving its efficiency. And the direct observation of short-lived chemical intermediates by spectroscopy is playing a growing role in uncovering the individual steps of the four-electron catalytic cycle. Vibrational spectroscopy, that's infrared or Raman spectroscopy, provides molecular-level details of the structure. And importantly, it allows us to monitor separately the individual steps of the four-step catalytic cycle. However, there is a crucial piece of insight additionally needed, and that is understanding the mechanism by which the sequentially delivered charges to the catalyst drive the catalytic cycle. That's because any bottleneck in the delivery of charge to the surface intermediates that slows down and hinders the completion of the cycle will invariably degrade the efficiency, typically below what's needed to keep up with the solar flux at maximum solar intensity, so around midday. So in this perspective, we focus on recent insights from spectroscopy, infrared and Raman spectroscopy, and accompanying time-resolved optical spectroscopy on how these charges delivered to the catalyst drive the cycle. The most direct mechanistic information requires that the time resolution of the spectroscopy is high enough so that the true kinetics of the intermediate is recorded, which is extremely rarely the case. Only a few studies right now exist with that qualification, and only about the initial steps of the catalysis. Therefore, an important question addressed right up front in the article is what types of measurements are required to prove the kinetic relevancy of an observed surface species. That is, how do I know that an observed surface species is actually part of the kinetically relevant cycle that produces the oxygen when I don't know really the exact kinetics of that intermediate? Through time-resolved studies, the dominating and rate-boosting role of random encounters of 2 or 3 surface charges in the form of rapidly hopping metal oxo or oxyl groups was discovered. And these encounters give access to a very low barrier OO bond formation to a water molecule. Now, spectroscopic studies and kinetic rate law studies have uncovered the crucial role of this hopping of the surface charges in driving the water oxidation catalysis, giving access to these random encounters which consequently pull the charge and give access to the low barrier OO bond formation. So that's the mechanism by which the delivered charges to the catalyst drive the cycle. Now, looking into the future, new spectroscopic techniques based on laser techniques are emerging, as well as new techniques for triggering heterogeneous electrocatalysis. And these open up higher sensitivity and better time resolution for the vibrational spectroscopy. So with these new techniques and new tools, and also ultra-fast X-ray free electron laser spectroscopy and monitoring of the dynamics of the metal electronic state, the coming years should really show a much more complete picture of the mechanism of water oxidation, the important reaction for making solar fuels.